In the lesson today, we will continue with Poisson distribution, and we find a recurrence relation between two consecutive terms. We'll use this relation to find the mode of the distribution, and we'll see how the parameter changes when the conditions under which we measure change. Let us remember then, when x is distributed following a Poisson distribution, to calculate the probabilities, I use this formula. Now the question is, what's going to be probability of x equals k plus 1 over probability of x equals k? With this, I want to see if the shape of the distribution increases or decreases. Now, probabilities are positive numbers, right? So if this expression is bigger than 1, then probability of x being k plus 1 will be bigger than probability of x being k. So when you start drawing it, it will go up. If this one is smaller than 1, then the graph will go down. So let's see what happens with this probability. So I'm going to calculate this expression. Pause the movie and try yourself to do the algebra required. So we observe that probability of x being k plus 1 is lambda over k plus 1 times probability of x being k. This tells me that, for example, probability of x being 1 is lambda over 1 times probability of x being 0. And probability of x being 2 is lambda over 2 times probability of x being 1. And so on. It is called a recurrence relation because I can find probability of x being 3 if I know probability of x being 2. And so on. However, in questions, I recommend you to use this formula. Now, look at lambda and at this expression. This will give me the shape of the distribution. If the denominator is about lambda, the same about lambda, then this probability stays the same almost. Therefore, is going to be a peak of the shape of the distribution. So imagine this one is probability of x being k, and this one is k. Probability of x being 0, we start from 0, if I replace in the formula, is e to the power of minus lambda. Lambda to the power of 0 was 0 factorial, so it's e to the power of minus lambda. And that's probability of x being 0, somewhere here, positive. Probability of x being 1 is lambda times this one, so I multiply by lambda. Now let's assume lambda is bigger than 1, so it's going to be bigger. Probability of x being 2 is going to be bigger, and so on, until at one point where this one is going to be about 1. And this is going to be the peak. Then, if the denominator gets bigger, lambda over something big, it will get smaller. And that's how we have the shape of the distribution. Now the mode will be about where lambda equals k plus 1. So lambda where about is k plus 1 will give me the mode. Now lambda is not necessarily a whole number, but k needs to be a whole number to find the mode. So it might happen that the shape of the distribution looks like this. So the top is somewhere here, but we need to find a integer lambda, so it's either here or here. That's why after we find where about is k, we'll need to calculate both to see which one is higher, and that's how I find the mode. Now let us try this question. If x is Poisson of lambda, and we know that probability of x being 4 is 1.2 times probability of x being 3, well, if I use the previous relation, probability of x being 4 is lambda over 4 times probability of x being 3. Therefore, lambda over 4 is 1.2, so lambda is 4.8. What is the mode of x? The mode of x is about where lambda is k plus 1. So k, it's about 3.8, but k cannot be decimal, so we are looking for probability of x being 4, probability of x being 3 to see which one is bigger, and that one is going to give me the mode. Now I replace using e to the power of minus lambda times lambda to the power of x over x factorial, and I calculate both of them using the formula. Now I calculate probability of x being 4, probability of x being 3 is smaller, right? So probability of x being 3 is smaller than probability of x being 4. And in order to make sure, I calculate the probability of x being 5 as well, and it gives me something smaller. So therefore, x equals 4 is the mode. One thing that we established experimentally is that for a variable that is distributed Poisson of lambda, the expected value is lambda and the variance is lambda as well. The proof of this is beyond your syllabus. Now, if x is Poisson, and that's an interesting fact, if x is Poisson, then it follows that e of x is the same as var of x. But if e of x for a certain distribution is not equal to var of x, therefore x is not Poisson. You are often asked in papers to prove that a distribution is not Poisson. The only tool you have to prove is by finding e of x, var of x, and showing that they are not equal. Therefore, it's not Poisson. However, if e of x is the same as var of x, it doesn't mean that it's Poisson. We just don't know. It might be or not. So pause a bit and think of these statements. I will exemplify the last concept of this lesson through a question. Please pause the movie and try it yourself. Now, when I see a question in stats, I start by reading it and modeling with mathematical notation. Number of emails Serena gets can be modeled by a Poisson distribution with a mean rate of 1.5 per hour. So let x be the number of emails Serena gets per hour, and it's very important to define all the variables, so per hour. Then x is Poisson distributed with a mean at 1.5 in 1 hour. AI. What is the probability that Serena gets no emails between 4 and 5 p.m.? So this is within 1 hour. And then I replace and I find e to the power of minus 1.5 times 1.5 to the power of 0 over 0 factorial, e to the power of minus 1.5, and I use my calculator. What is the probability that Serena gets more than 2 emails between 4 p.m. and 5 p.m.? So is probability of x being bigger than 2? Remember we said all probabilities of 0, 1, 2, 3, 4, all that they add up to 1. If I want this one, it's going to be 1 minus probability of x being 0 minus probability of x being 1 minus probability of x being 2. And I'm going to calculate this later. What's the probability that Serena gets one email between 6 p.m. and 6:20 p.m.? That's very interesting because between 6 p.m. and 6:20 p.m. they are 20 minutes, so it's a third of an hour. If the mean is 1.5 per hour, then in this case the mean will be a third of it, so it's going to be 0.5 as a mean. So I'm going to say let y be, because it's another variable, the number of emails in 20 minutes. And here is a new concept, and y is Poisson of 0.5. And I need to find probability of y being 1, exactly 1 email. And I'm going to use a formula. So when the time or space changes, then the mean of the distribution changes accordingly, proportionally. I'm going to let you try the next question. More than 2 emails in an hour, exactly twice in a 5-hour period. Okay, let's stop and try together. It's very interesting. Okay, let's look at question B. What's the probability that Serena gets more than 2 emails in an hour, exactly twice in a 5-hour period? So I have a 5-hour period, first hour, second hour, third hour, fourth hour, and fifth hour. That's how my 5 hours period. She needs to get more than 2 emails in exactly twice, either here, or here, for example, exactly twice. You see the binomial distribution? So I would say let T be number of successes within 5 trials. So the trials are the 5 hours, and success will be more than 2 emails. So then T is binomially distributed with N and P, more than 2 emails. And I need to find probability of T exactly twice. T was 2. So that's going to be 5 combination 2, number of successes, probability of success to the power of 2, probability of fail to the power of 3. And see how the binomial is combined here with the Poisson distribution, and you need to recognize. That's why it's very important to label your distributions, give them a name, and tell what they are. So I had here 3 distributions. Question C. Would it be possible to use Poisson distribution to find the probability that Serena gets no email between 4 a.m. and 5 a.m.? Yeah, probably it is, but not this Poisson distribution, because this it's not the same experiment. Between 4 p.m. and 5 p.m. Serena gets some emails, but in the a.m. probably she will not get. So it might be possible, depends on her time zone, depends on what she works. Does she work cross countries and then she expects to get emails there? Or does she not work cross countries and within her country she gets no emails here? So it is possible, but not using that Poisson distribution above.